dawn of the 19th century, the golden age of chemistry. The new science was about to turn the old on its ear. Science had banished the alchemist and replaced his hocus pocus with the beginnings of a workable atomic theory and tables of atomic masses. These were heady times. With their new methods of quantitative analysis, chemists were confident of unlocking the secrets of matter, except for one very mortal barrier. Even a goat outclassed the best of their laboratory efforts, because a goat could produce an organic substance, milk. Try as they might, chemists could not synthesize biological products. No mix of elements, no technique resulted in a single organic substance. Chemists shrugged off defeat by suggesting that the vital flame in living organisms was needed to spark organic compounds into existence. But this theory of vitalism was to have a short shelf life. In 1828, the German chemist Friedrich Wöhler stumbled upon something only the prepared mind could seize. Heating an inorganic substance, ammonium cyanate, he produced crystals, identical to crystals he had seen in urea. With his declaration, "Urea without the kidney," he shattered the theory of vitalism. Now, chemists scrambled to isolate organic substances and quickly identified a bewildering array of organic formulas. So bewildering that Wöhler threw up his hands and decried, "Organic chemistry is a dreadful jungle with no way out." Still, without a roadmap, chemists did come across signposts. Carbon was the common factor in organic compounds, and only a few other elements, such as hydrogen, oxygen, and nitrogen, were involved. Chemists were, however, perplexed by the large number of atoms forming organic molecules. The clearing was hacked out mid-19th century by another brilliant German, Friedrich Kekule. Theorizing that there was no distinction between organic and inorganic substances, he assigned to the so-called organic carbon a valence of 4, the same as its inorganic species. At the time, valence meant the power of an atom to combine with another atom. Since methane had been massed, Kekule knew its molecular formula, or the combining ratio of its two elements. He speculated that carbon, with a valence of 4, and hydrogen with a valence of 1, bonded in this manner. As for ethane, he proposed that carbon linked up with another carbon atom, while the remaining valences were satisfied with 6 hydrogen atoms. Structures began to emerge. One molecular formula could account for straight chains and branched chains as well. But they weren't out of the jungle yet. Benzene, a stable compound with molecular formula C6H6, just didn't mesh with his proposed structural models. So, as any self-respecting chemist would do, Kekule slept on the problem and dreamed of atoms twirling like a snake until it seized its own tail. Eureka! With a flash of insight, he envisioned carbon atoms forming a ring, double bonded in this stable configuration. Kekule's elegantly simple structural formulas and his notion that carbon forms 4 bonds, now called covalent bonds, have stood the test of time. To answer what covalent bonds are and why carbon forms them, we must probe deeply into the structure of the atom. In this program, a two-dimensional planetary model is most useful for our purposes. An atom consists of a nucleus containing positively charged protons surrounded by shells of negatively charged electrons. In helium, for example, 2 electrons circle the nucleus, the maximum allowable for the first shell. Neon possesses 2 electrons in its inner shell and 8 in its outer shell, the maximum permissible for the second shell. These atoms are self-sufficient and extremely unreactive. Lithium, like helium, contains 2 electrons in its inner shell, but only 1 electron in its second shell. Lithium then has a strong tendency to shed this electron in order to attain the stable electron configuration of helium. Enter fluorine. With 7 electrons in its outer shell, it's eager to strip an electron from lithium and attain neon's stable configuration. Lithium fluoride, an attraction of opposites, a marriage made in heaven. In molecular bonding, the measure of an atom's ability to attract electrons is referred to as electronegativity. On the periodic table, lithium, with its loosely held outer shell electrons, is assigned a value of 1. Fluorine, with its more tightly held outer electrons, an electronegativity value of 4. Carbon, halfway between the 2 extremes, has an electronegativity of 2.5. Its inner shell contains 2 electrons and its outer shell 4. Carbon appears to have a choice in attaining maximum stability. Shed 4 electrons in order to resemble the lean, mean helium, or snap up 4 additional electrons and attain the heavyweight status of neon. But neither option is open because carbon's 2.5 electronegativity is too strong to relinquish 4 electrons and too weak to strip 4 electrons from other atoms. So in order to gain the stable configuration of neon, carbon compromises. It time-shares electrons with other atoms. Except time-sharing occurs nearly at the speed of light. The covalent bond, then, is defined as sharing a pair of electrons. Kekule had it right over 100 years ago, and his seminal idea is still the cornerstone of organic chemistry. While this two-dimensional modeling is still useful, it has been superseded by three-dimensional models, which we will explore in subsequent programs.